In these sessions, I'd like to show you the energy state of oscillational motion, harmonic oscillators. So example of the harmonic oscillator is the hydrogen molecules. In the hydrogen molecules, two protons are bound together. Two protons move as they are bounded by strings. So hydrogen atoms oscillate around their equilibrium positions. In the harmonic oscillator, force is expressed minus kx. X is the distance from the equilibrium point. K is a proportional constant. K is a positive quantities. Potential energy is expressed 1 over 2 kx squares. If you remembered classical physics, ma equal F, ma equal minus kx. Then solutions of these equations express the trigonometric functions a sine omega t plus b cosine omega t. Omega is expressed as square root k over m. So this means k is expressed m omega squares. So instead of k, we can use the m omega squares. Then potential energy is expressed 1 over 2 m omega square x squares. So in quantum physics, instead of k, we use the m omega squares. Okay, so potential energy is expressed 1 over 2 m omega square x squares. So Schrödinger equations, in that case, is expressed these equations. Minus h bar squares over 2m times second derivative of c with respect to x plus 1 over 2 kx squares c plus e c. Left hand side is equal to the energy. This energy, so this means energy is expressed p squares over 2m plus potential energy. So if you compare with these two cases, so p squares is expressed minus h bar squares second derivatives. So from this equation, actually you can express the p is expressed with the first derivatives h bar over I times derivative. So p is expressed with the operators. We call this the momentum operators. So equations is expressed 1 over 2m times p square plus m omega x squares equal e(c). Schrödinger equation becomes really simplified. h(c) equal e(c). We call h is a Hamiltonians. Okay, so we are going to solve these equations. So this is second order differential equations. We could solve these differential equations using the techniques we learned advanced mathematical lectures. But in these lectures, I use a different method to solve this differential equation. First of all, we'd like to study the commutators. This definition of the commutators of operators A and B is given by this equation. AB minus BS. To find out the commutators of the operators, you need to add the trial function of the f. Then find out the commutators of the operators of the A and B's. And we'd like to find out the x and p. So I'd like to show you the x, p, the commutators. Then add the trial functions, fx. Then this part is xp minus px fx. Then substitute p. Definition of p is x h bar over I. First derivatives d dx minus h bar over I d dx x fx. Then we'd like to expand this parenthesis. It becomes x h bar over I df dx. And the second, you have to be careful. This is d dx. So x f. So when you try to calculate the second terms, you are actually the derivative is appears before the x f. So we can apply derivative of the product of the two functions. So this part is expressed f plus df dx. Then second term is going to be cancelled out. So this term is going to be cancelled out. So it becomes minus h bar over if. So you can write this is ih bar f. And by comparing except the trial functions, so we discovered commutator of the x and p is expressed ih bar. Okay, so we derived commutator of the x and p is ih bar. Okay, using this method, you can find the commutator. To solve the Schrödinger equation of the harmonic oscillators, we'd like to introduce the ladder operators. Ranging operators is a sub plus. This is definition of the ranging operators. You will know that why we named these operators as ranging operators. And the lowering operators, a sub minus, these operators. Then we'd like to consider a sub minus a sub plus. A sub minus a sub plus. This is, you can write an square root 2h bar m omega times ip plus m omega x times 1 a sub plus square root 2h bar m omega minus ip plus m omega x. So square root 2h bar m omega is a constant values. You can multiply. Becomes this one. So for the ip minus ip, this becomes p squares. For the multiply m omega x plus m omega x squares. The last one is the cross terms. ip m omega x. So this becomes plus ip m omega x minus this part minus m omega x ip. In this case, the p appears first and the x. This is x and p. So you can look at this is minus I m omega is constant. This is xp minus px. This is exactly equal to the commutators of the xp. And the commutator of the xp, we have discovered this is ih bar. And then this part becomes plus m omega h bar. So finally, this is 1 over 2h bar m omega p squared plus m omega x squared plus 1 over 2. So because of the m omega h bar times this one, this becomes 1 over 2. I have explained this one. Also use the same method. We have these relations. We could discover this becomes a minus a plus minus a sub plus a sub minus. We can substitute. This is here and this is going to be here. So it becomes 1. I introduce ladder operators. This operator is very useful to study harmonic oscillators in the Schrödinger equation. This is the end of this session.